to this HP Expert 1 presentation. In this video we're going to discuss spanning tree. Spanning tree has been developed to stop layer 2 loops that occur in switched environments. Spanning tree has been around for many years and there have been a lot of developments and enhancements to this protocol. So one of the challenges is to understand the differences between the various implementations of spanning tree. Because of the amount of content, this video has been split into two parts. In the first video, we're going to look at the basics of spanning tree, and in the second video, I'm going to show you more complicated topologies and the advantages of the more enhanced versions of spanning tree. Let's get started. 802.1d is an IEEE standard originally published in 1990. This was in the days when bridges were used rather than switches. So some of the terminology that we use is related to bridges, but switches today have replaced bridges. Switches use ASICs or application-specific integrated circuits to provide features and functions in hardware rather than in software. Bridges, on the other hand, used software-based processes. So 802.1d is the original version of spanning tree, and in this first video, I'm going to explain the basics of 802.1d. I'll also mention some of the other spanning tree implementations, but in the second video, we'll discuss them in more detail. Cisco developed per VLAN spanning tree or per VLAN spanning tree plus to try and enhance 802.1d. The difference between PVST and PVST plus is that PVST is only supported on ISL links rather than on 802.1q. PVST Plus supports both ISL and 802.1q. These days, ISL is generally not used, and thus today we use PVST Plus and not PVST. 802.1w or rapid spanning tree enhances spanning tree for more rapid convergence. Cisco integrated that with PVST, and thus we have a rapid PVST Plus. Multiple spanning tree, or 802.1s, also enhances spanning tree by using instances to provide load sharing and other advantages. So let's get started with the basics of spanning tree, and then we'll talk about the different implementations and versions of spanning tree. Let's start with a very simple topology to explain the reasons to implement spanning tree. Why is spanning tree required on a switched network? So this topology will allow A to communicate with B and vice versa. The problem, however, in this topology is what happens if this link goes down. If the link between switch 1 and switch 2 goes down, there's no communication. So what's often recommended in networks is to implement some type of redundancy. So in this topology, we could expand it to include an additional link between the two switches. So in this case, port 3 is connected to port 3 on switch 1 and switch 2. So we've added redundancy to our topology, but this introduces other issues or other problems. The issue is if A sends a frame to B, what will happen with that frame? And to help explain this, let's also view the MAC address tables of the switches. So this is the MAC address table of switch 1, and this is the MAC address table of switch 2. Let's assume in this topology that the switches have rebooted, so their MAC address tables are empty. When A sends a frame to B, the destination address will be B, and the source address will be A. So A is sending a frame to B, and when it arrives at switch 1 will read the source address in the frame and update its MAC address table to show that A is on port 1. MAC address B, however, is not in the MAC address table, so the switch will flood the frame out of all ports. Now this is a very simple topology. There are only two interfaces. But if this was a switch with many ports, a frame coming in on one port may be replicated or flooded out of 40 other ports. So what does switch 2 do? It receives a frame on port 1, destination address is B, source address is A. What is the switch going to do with that frame? Well, the first thing it's going to do is update its MAC address table to state that A is on port 1. and then it's going to flood that frame out of all ports. B will receive the frame from A. However, switch 2 also receives the frame on port 3. And now this is where it gets a little confusing. Is A on port 1 or is A on port 3? The switch will also flood the frame out of all ports. So the frame received on port 3 is flooded out of port 1 and port 2. B has now received the frame twice. Once when it originally came in on port 1, and now when it came in on port 3. So it gets confusing for the end devices. The MAC address table is changing. The first frame that arrived on port 1 allowed the switch to update its MAC address table stating that MAC address A is on port 1. The second frame that arrived on port 3 now indicates to the switch that A is actually on port 3. Now that's an issue because we have MAC address table instability, as well as the devices that are receiving the frames multiple times. But it gets worse. When the frame arrived on port 1, it is flooded out of all ports. The frame is sent back to switch 1, and when it arrives on switch 1 updates its MAC address table to state that A is on port 3, as well as flooding the frame out of all ports. So in this case, A has received its own frame. But the biggest issue is this: the frame is being sent back to switch 2. Switch 2 then floods the frame out of all ports. And hopefully what you'll notice here is that a loop is forming. The frame is being flooded round and round and round and round. We have a loop on the network. Now this can get so bad that the CPU utilization of the switches and end devices shoots up as this frame is replicated round and round and round. The same problem occurs in the reverse direction. This frame is looped round and round and round as well. A single frame is now being duplicated many times. And this is aggravated when you have many interfaces. So a single frame coming in could be replicated 40 times, for example. There's an exponential increase of traffic on the network. What ends up happening in a broadcast storm or a loop like this is that frames loop round and round and round, consuming bandwidth and network resources. This issue is very common with what's called a broadcast storm. When A sends a broadcast, now a broadcast frame consists of 8 Fs at layer 2 in the OSI model. A broadcast is meant to go everywhere, so a switch will flood the broadcast out of all ports within the same VLAN. Once again, you have this issue where the frame loops round and round and round, possibly bringing the network to its knees. Loops like this can force network engineers to have to try and troubleshoot by removing cables until the loop is broken. This is not ideal in a mission-critical network. So Spanning Tree was developed to stop loops. Just take note once again that Spanning Tree was developed many years ago when networks were a lot slower and less mission-critical than they are today. So the premise for Spanning Tree was to stop loops, not necessarily to converge quickly. So one of the major issues we face today with Spanning Tree is speed, or lack thereof. Spanning Tree is very slow by today's standards. But now let's discuss how Spanning Tree stops loops in switched environments. When switches start up, they send out what are called Bridge Protocol Data Units, or BPDUs. That's how the switches discover one another and can then elect a root bridge or root switch. So in 802.1d, common spanning tree or mono spanning tree, the first decision is to elect a root bridge or root switch. One device in the layer 2 topology is chosen as the root device. Think of a tree in the physical world. A tree cannot survive without a root, and Spanning Tree cannot survive without a root. So the root of Spanning Tree is of great importance. The root switch or root bridge is determined based on two criteria. The first one is lowest priority. The default priority is 32768. This can be changed on individual devices to ensure that certain devices become the root rather than other devices. So the first decision is lowest priority. The second decision, if the priorities are the same, is lowest MAC address. So if the priorities of the devices in the layer 2 topology are the same, the lowest MAC address is used as a tiebreaker. Now the priority can vary with certain implementations of spanning tree. In 802.1d, the priority is always 32768. But on per VLAN spanning tree or PVST, the priority is by default 32768 plus the VLAN number. So using VLAN 1 as an example, the default priority would be 32769 when using PVST+. Once a root bridge has been determined in the topology, all other switches that are non-root bridge switches choose what's called a root port. A root port is their best port to get back to the root bridge. A single port is chosen in 802.1d. So one port per switch is chosen as the root port. The root port is determined using various criteria. The first choice is lowest path cost, which is an inverse of the speed of the link. There are various values used by different implementations of spanning tree, and I'll show you some examples in a moment. But just note, the lowest path cost is used to determine which port is the root port. Essentially, the quickest or best link back to the root bridge would be used as the root port. If that cannot be used as a deciding factor, a neighbor switch with the lowest bridge ID is chosen. The bridge ID consists of the priority and MAC address of a switch. So the neighbor that has the lowest bridge ID, in other words, lowest priority or lowest MAC address, will be used to determine the root port of the local switch. If that can't be used, then a port with the lowest priority is chosen. The default priority is 128, and if that can't be used to determine a root port, then the port with the lowest port ID will become the root port. In other words, port 1 is chosen in favor of port 2. Port 2 would be chosen in favor of port 3, and so forth and so on. So port 1 would be chosen if no other criteria can be used to determine the root port. What you may notice is that some of the options used to determine root port as well as root switch in spanning tree are fairly random. And to optimize spanning tree, you're going to want to influence some of these criteria, specifically the choice of the root switch. But you may also want to influence root port selection. Once the root ports of switches have been chosen, the next selection criteria is to elect designated ports, and this is done on a per segment basis. The decision criteria is very similar to root port selection. The first option is to choose the port that has the lowest path cost back to the root. So on a per segment basis, a port is chosen that is the best port to use back to the root switch. Now I will be showing you various examples to show you how spanning tree does this, and I'll refer back to this selection process. But for now, just note that the designated port is selected on a per segment basis. Typically it's the port with the lowest path cost back to the root. Also note that a port on the root switch or root bridge has a path cost of 0. So ports on a root bridge are always going to be designated ports on that segment. If that can't be used, then lowest neighbor bridge ID is chosen as a tiebreaker, and if that can't be used, lowest port priority and lowest port ID. Once the root bridge is chosen, root ports are chosen, and designated ports are chosen, all other ports are set to the blocking state. Only specific protocols such as LLDP or Link Layer Discovery Protocol and BPDUs or Bridge Protocol Data Units are transmitted and received on blocking ports. normal user traffic is blocked on that port. And that's how spanning tree stops loops in a switched environment. So let's look at some examples to work through the process. We'll start with some simple examples, and in the second video, I'll show you more complicated examples. An important default to be aware of is that on HP switches running either the COMware operating system or the Provision operating system, spanning tree is not enabled. So by default, be careful when plugging in cables between HP switches. Spanning tree is not enabled by default. So if there are multiple paths in a switched network, a broadcast storm could occur. On Cisco switches, by default, spanning tree is enabled, but on HP switches, be aware spanning tree is not enabled by default. So you may want to enable spanning tree before connecting redundant links. Now, how do switches learn about one another? As mentioned, bridge protocol data units or BPDUs are sent out of all ports on HP switches by default every 2 seconds. So the switches will learn about each other when they receive BPDUs on their ports. As an example, switch 1 will know that there's a loop because it's receiving a BPDU from switch 2 on port 2 as well as port 3. So BPDUs from a switch with the same bridge ID are received on multiple ports. Thus switch 1 knows that there's a loop. By the same token, switch 2 will also know that there's a loop because it's receiving a BPDU with the same bridge ID on port 1 as well as port 3. The first thing the switches do is elect a root bridge. By default, when a switch starts up, it believes that it's the root. But as a switch receives BPDUs, it'll learn that there are other switches in the topology, and an election will then take place to determine who the root is. So the election once again is done on lowest priority. The default priority is 8000 in hexadecimal or 32768 in decimal. If a decision cannot be made on priority, then lowest MAC address is used as a tiebreaker. So the first decision is to determine who the root switch or root bridge is. In this topology, the priority of this switch has been lowered to 4096. Switch 2 is using the default priority of 32768. So in this topology, switch 1 will become the root switch because it has the lowest priority. The next decision is to determine root ports. Root ports, once again, are determined using the following criteria. One port is chosen on each switch that's not the root bridge based on the path cost. The path cost is an inverse of the speed of the link. The higher the speed of the link, the lower the path cost. The path costs will be added if there are multiple links between this switch and the root bridge. Then it's based on lowest neighbor bridge ID, then port priority, and then lowest port number. So going back to our topology, switch 2 has 2 paths. It can either use port 1 or port 3. Now let's assume that all the links are gig interfaces. Which port will be the root port of switch 2? Here's an example of the path costs used by multiple spanning tree. This is the default spanning tree used on HP switches. So I'm just going to show you these path costs. Cisco, for example, has different path costs when using PVST. So on a device running the HP Provision software, a fast Ethernet interface has a cost of 200,000, gigabit 20,000, 10 gig 2,000, and these are the default costs on an HP Provision switch. When using multiple spanning tree, which is the default spanning tree that's enabled when spanning tree is enabled on the switch. Cisco uses the same costs, so 200,000, 20,000, 2,000. These are the default costs when multiple spanning tree is used. On HP COMware devices, the costs are 200, 20, and 2, so they're different. So it's recommended that you set your switches to all use the same path costs. If I'm using miles and you using kilometers, our calculations may be different. So rather standardize on one or the other. So in this case, the command stp path cost standard .1t configures an HP ComWare switch to use the same costs as Provision and Cisco. The best practice, once again, is configure the switches to use the same costs. So in our topology, we're using gigabit interfaces. So the cost would be 20,000, assuming that we've configured the ComWare switches to use .1t costs. In other words, the industry standard values. So in this topology, the path cost is 20,000 and 20,000. Path costs cannot be used to determine the root port. The next decision is to use neighbor bridge ID. But both these cables connect to the same switch, switch 1. So neighbor bridge ID cannot be used to determine the root port. The decision after that is port priority. The default priority is 128. So let's assume that the priority is still at default, so that can't be used to determine the root port. So the last choice is to use port number to determine the root port. Port 1 is a lower number than port 3, so in this case, port 1 will become the root port on switch 2. Once the root port is determined, the next decision is to choose designated ports on a per segment basis. So on this segment here, imagine that there's a device in the middle of this cable. Now that obviously doesn't exist, but just imagine that there is a device in the middle of the cable. Would it be better to go left to get to the root switch or to go right? And I think the answer is fairly obvious. It would be better to go left rather than right. It's going to be quicker to go here than to go here to get to the root bridge. So in this case, port 3 on this segment is the designated port. By the same token, port 2 on the other segment is the designated port. These ports are designated ports. Those are the ports to use on that segment to get to the root bridge. All other ports will be blocked. So in this topology, port 3 on switch 2 is blocking. Traffic such as LLDP and BPDUs are transmitted and received on this port, but other traffic is blocked. So traffic from PCA to PCB will traverse the upper link. No traffic will be sent through port 3 on switch 2. Spanning tree has successfully stopped the loop in this topology. Just to emphasize, designated ports and root ports forward traffic. So traffic is transmitted and received on designated and root ports. No user traffic is transmitted or received on a blocking port. Only certain protocols such as LLDP and BPDUs are transmitted and received on that port. Spanning tree has successfully removed the loop in this topology. In spanning tree, decisions are based on timers, and a port will only transition to the forwarding state after a set amount of time has elapsed. These timers come from an era when bridges were used rather than switches. A lot of these timers are not good enough in today's networks. And as I'll explain in video 2, rapid spanning tree allows for quicker convergence. But with 802.1d and PVST, these timers are used. You can reduce these timers, but you need to be careful. Spanning tree was designed to stop loops, not necessarily converge quickly. If the timers are reduced, inadvertently you may introduce loops in your topology. So it's recommended that you don't change these timers. In today's world, however, rapid spanning tree or multiple spanning tree is used, so these timers are not as important. However, just for understanding, it's well worth remembering the timers. When a switch starts up, all ports are put into the blocking state. User traffic is not transmitted or received. The MAC address table of the switch is not updated, but BPDUs are detected. This lasts for what is known as the max age timer, which is equal to 20 seconds by default. The switch uses this time to detect if any other switches are connected to it. It makes sense for the switch to start up with all ports in the blocking state, as this will prevent loops in a topology. After 20 seconds, the port will transition to the listening state, which will last for a period of time known as the forward delay, which is 15 seconds in length. In the listening state, BPDUs are transmitted and received. No user traffic is transmitted or received. The port is essentially still blocking in the listening state. The MAC address table is still not updated on the switch. During the listening state, the root bridge is elected. Root ports are chosen, and designated ports will be chosen. So the root bridge is chosen, one per topology in 802.1d. A root port is chosen, one per switch, that's not the root bridge, and a designated port is chosen on a per segment basis. The port will then transition to the learning state, which lasts for a period of 15 seconds, also the forward delay. BPDUs are transmitted and received in the learning state in a similar way to the listening state, but in addition, the switch is updating its MAC address table with MAC addresses learnt from devices. This reduces the amount of flooding that takes place in a topology when the port moves to the forwarding state. Flooding would occur when traffic to an unknown MAC address is received. So during the learning state, the switch is learning where devices are in the topology. Once again, no user traffic is transmitted during the learning state, but for this period of 15 seconds, the switch can learn where devices are in the topology. Ports that are not chosen as root ports or designated ports would transition back to the blocking state. So those are the ports that are blocked in the topology. Root ports and designated ports then transition to the forwarding state and will thus transmit and receive user data. Another state to be aware of is the disabled state. This is where an administrator has manually shut down an interface on a switch. Because the port is shut down, no traffic is transmitted or received. This is known as the disabled state in spanning tree. The port is thus disabled or shut down. Various enhancements have been made to spanning tree to reduce the time of convergence in a switched environment. A standard port may take 30 seconds to converge, and that's not acceptable in many cases in modern day networks. A PC booting up may need to connect to a DHCP server and receive an IP address from that DHCP server. However, when the PC connects to this port on switch 1, it could take 30 seconds for spanning tree to start forwarding on that port. So to increase performance, ports connected to edge devices such as PCs and servers are configured as edge ports in spanning tree. Cisco uses the term port fast. HP uses the industry standard term edge ports. It's important that you only enable edge ports on access ports or untagged ports and not trunk ports. In other words, you shouldn't enable edge ports on links between switches, because that may introduce loops in your topology. An edge port forwards immediately by bypassing the listening and learning states. So it goes directly from blocking to forwarding, bypassing both listening and learning. That allows for much quicker convergence, because rather than waiting for spanning tree to go through the various stages, blocking, listening, learning, forwarding, it immediately starts forwarding. So very quick convergence rather than taking 30 seconds. Spanning tree is still running on that port, but it transitions immediately to forwarding. If for some reason a BPDU was received on an edge port, that port can transition back to the blocking state, and it's good practice to do that. Spanning tree requires that each switch have a unique bridge ID. In the past, this consisted of a bridge priority and MAC address. The bridge priority was 2 bytes in size and the MAC address 6 bytes in size. Thus, the bridge ID is 8 bytes in length. When configuring multiple VLANs and running per VLAN spanning tree, a different MAC address had to be allocated for each VLAN. PVST creates an instance on a per VLAN basis, so to ensure that the bridge ID is unique, a different MAC address would be allocated. That worked fine when there were only a few VLANs, but if you're configuring hundreds or thousands of VLANs, this is not scalable. Vendors would need to assign a unique MAC address on a per VLAN basis. So in theory, if 4094 VLANs were supported, 4094 unique MAC addresses would need to be assigned to each switch. This was changed to conserve MAC addresses, also called MAC address reduction. Now with the extended bridge ID, the bridge ID is still 8 bytes in size, but the bridge priority is now split into 2 parts. So the 2-byte bridge priority now consists of a 4-bit bridge priority and a 12-bit extended system ID. The MAC address is still 6 bytes in size. So previously, when the bridge priority was 2 bytes in size, you could set the priority of the switch to 1. However, now, because of the change in the fields, the first 4 bits are priority and the remaining 12 bits are extended system ID. So if the priority bit is set to 1, the value when calculated is 4096. In other words, this field as a full field is 4096. If the priority is set to 2, the full field equates to 8192. On Cisco switches and HP switches running the Comware operating system, you have to configure the bridge priority in multiples of 4096. On HP switches running the Provision operating system, when you configure a bridge priority of 1, it automatically converts it to 4096. Or if you set the bridge priority to 2, it converts it to 8192. So on HP switches and Cisco switches today, the bridge priority needs to be set in multiples of 4096. So on HP switches, the default priority is 32768. On Cisco switches, when running PVST+, the switch priority is equal to the priority plus the VLAN number. So for VLAN 1, the priority is equal to 32769. In other words, 32768, the bridge priority plus 1 for the VLAN number. For VLAN 2, the priority would be 32770, and so forth and so on. So on HP switches, the default switch priority is 32768. On Cisco switches running PVST, it will vary because the VLAN number is added to the switch priority. That concludes this first video discussing spanning tree. In the next video, we'll look at spanning tree in more detail in a more real-world topology. For more information, please visit hp.com/go/expert1.